Okay, so we've finished this problem. What we have seen here is an example of an equilibrium problem, but it's also really fundamentally an example of a simple machine, of a lever. So simple machines, which of course was the nominal topic for today's lab, are devices that make it easier to do work. It's real important to be clear. Simple machines don't do more work than you do on them. In fact, because life is never perfect, a simple machine is probably going to absorb some energy, so it's going to do less work than you do on it. So you lose energy by using the simple machine. But what it gains you is it allows you to move a heavy object with a smaller force. So it multiplies force, but does not multiply energy. So what we had here was a lever, and the lever was based on the sum of the torques about the fulcrum is 0. So you sum the torques about the fulcrum, and you set it equal to 0, and you find a relationship between the distances and the forces. So in the last line here, I did essentially the work you had to do. Now, I really apologize I honestly had the words I wanted on that problem, and then I copied it to another place, and I went to change the other place, and I actually changed the original. And then, yes, it's a complicated process, but it wasn't the way I had planned it. But we did the sum of the torques is equal to length 1, force 1, minus length 2, force 2. One's positive, one's negative because of the directionality. And since the sum of the torques is 0 in equilibrium, I can solve this for the ratio of the forces, and the ratio of those forces is equal to the ratio of the lengths. But do notice it's force 2 over force 1 is equal to length 1 over length 2. And so we call this thing here the mechanical advantage. Or MA for short. It said mechanical advantage on that problem. It wasn't supposed to. That was part of me not undoing everything when I had started changing. So the mechanical advantage, force 2 over force 1. That's the ratio of the force I'm going to get out to the force I have to put in. But that's equal to length 1 over length 2. Now, if we wanted to calculate work, the work would be the same on both sides. So we're going to go straight into another problem, but this time I'm going to do the problem. So, of course, I started with PowerPoint, and I have to go back here to do the work. Suppose you have a mass of 85 kilograms and a 1.33 meter long pry bar, right? So pry bar, that's a lever. What mechanical advantage do you need, and where must the fulcrum be placed for you to just be able to lift a 400 kilogram object using your body weight? Now, I didn't do this problem beforehand, so I don't know how ridiculous the answer may or may not be. But we'll see. So first, what concept is involved? Okay, equilibrium. It's equilibrium, the special case of a simple machine. Why did I say the special case, the simple machine? Because I'm going to go straight to, yes, I'm now on your page instead of my page. It doesn't matter, right? I have things written differently for my presentation than I have for your handout, and I'm on the handout. That's okay. So I have the special case of the simple machine because on the preceding slide in the presentation, I went through and very quickly did the work you get from equilibrium to the simple machine result. And the simple machine result has the mechanical advantage. I'm just going to put MA. The mechanical advantage is equal to force 2 over force 1. And it's also equal to length 1 over length 2. Right, that's the last thing I had on the slide that we just came from. So that's an outcome of applying equilibrium to the simple machine of a lever. Now I have to draw a diagram. Never going to get away from those, right? So here's my lever, or if you're British, lever. There's my fulcrum. The fulcrum is the place you're pivoting. Here's my load. Force 2 is equal to the load, which it tells me is 400 kilograms times G. And then I'm going to have, I want it so I can just barely lift it if I'm hanging off of the end. So I'm going to have at this end, force of me, which is equal to my mass, I wish it was my mass, of 85 kilograms times G. What do I not have on here?
The forces around the fulcrum.
Okay, I don't have the forces on the fulcrum. I have the force of the fulcrum right there, and something that I don't list. I don't give you the mass of my pry bar. What does that mean to you?
Not needed.
Yes, it's massless. Is it really massless? No, of course not. But I could assume that the mass of that pry bar is very small compared to the forces that I'm getting otherwise, so that the force of gravity of the pry bar is inconsequential. So if I don't give it here, you just have to assume, okay, that must mean it's massless. If it's on a test, you know what to do? Raise your hand and ask me. Say, it doesn't give a mass for the pry bar. Do I need that? And then I would either say, just assume it's 0, or it doesn't matter, or oops, I forgot to give it to you. It'd be one of those responses, right? Don't go on the test and say, well, I'm just going to blindly hope. Okay, so we have, yes, sir? Yeah, the force fulcrum would be fundamentally the same as force normal. It's not, the fulcrum itself is touching the ground, but the plank isn't. Yeah.
What units does mechanical advantage in?
What are units of newtons divided by newtons? Nothing, that's right. So the mechanical advantage is unitless. There's one more thing here that I need on my figure that I don't have. Distances, I need the distances. So I have the total length is length equals 1.33 meters. And then I'm going to call this distance here x that I'm looking for. So there I've got my figure. Now I can move on. First question, what's the mechanical advantage I need? I can actually calculate that already. What's the equation for mechanical advantage? Force 2 over force 1. So what is it? You have somebody who's just already calculated it. It's going to be mechanical advantage is equal to the force 2 over force 1 equals 400 kilograms times G divided by 85 kilograms times G. Notice I never put in the 9.8 because what happens to my G's now? They cancel out. And so, what was it you got?
4 point, if you round up, it's 4.71. Yeah, 4.7.
If you, I hear you guys. Okay, so 4.7. Yeah, I only have 2 sig figs, so 4.7.
Okay, never mind.
So, was that hard so far? No. Okay, we're not done clearly, but so far that was pretty straightforward. Now it says calculate the necessary I'm supposed to do the work down below. Look, I'm magic. I can do the work down below. Look at that. Did it right where it's supposed to be. Using the mechanical advantage and the total length of the lever, calculate where the fulcrum must be placed. Well, what's my other equation for mechanical advantage?
Oh my goodness.
So length 1 equals length 2 times mechanical advantage. And I can look up here and say, well, length 1 is this distance here. And length 2 is this thing that I called x. So in terms of x, what is length 1?
1.13 minus x.
Yes. So I have so if I just plug that in here, I have well, now it's starting to get easy. Since my mechanical, well, let's just add x to both sides. L equals x times mechanical advantage plus 1, divide both sides by mechanical advantage plus 1. This,
What?
Oh, that's how.
You can't read what?
not as bad as when I was my first year of teaching, like first lecture, student just yells, "Hey, you can't do that." I can't. So I added x to both sides.
Wait.
I got it.
So I have L equals
I got it.
x times, I know you do, Max.
No, but I'm not there. There you go. That's
Oh,
what I meant.
okay,
That's what I
okay,
meant.
okay.
Then I factored out the x. Okay, so
That makes sense.
because I'm solving for x.
Because x divided by x.
Okay, I have x times ma, or as we like to say, max,
Right.
plus x. There's an x in both of them, right?
Right.
So that means I can put the x outside and put ma plus 1 all times x.
Okay, length 1, right, is the little length up there, that's gonna be 1.33 minus x.
Right.
And the other one.
I didn't know that.
And the other one was just x. Because I defined x as that distance. X was length 2.
Okay, wait. Wait, you have that as length 1, you have length 1 as 1.33 minus x?
Length 1 is equal to total length 1.33 minus x. And length 2 is equal to x. So,
Do we need to convert
Go ahead.
grams?
do I need to convert what?
Because, well, when we plug in the numbers and everything, won't that be meters, and so we need to convert it to centimeters? Or is that?
Yeah. Yeah. We haven't gotten to put any numbers, but yeah. So now with this relationship, I have L is equal to x times ma plus 1. So how do I get x by itself? Okay. Didn't want to assume, since I am not mocking you. That would not be appropriate. So x is equal to L over ma plus 1, putting in our numbers, 1.33 meters, or converting it to centimeters, what's 100? I'm really good at saying the answer when I mean to say the question. What's 100? What's 1.33 meters in centimeters? Yes. Divided by our mechanical advantage of 4.7 plus 1. And I should put, it was 4.71 or something, right?
Yes, 4.71.
Because keep an extra significant digit here so I don't lose. And so 133 divided by 5.71. Okay. Can you read my writing?
Yeah.
That was the issue though, right?
What?
I tried to do the inversion. We got that
What did you want? To draw the diagram? Are you good? I can't hear you, Isabel. Okay, can you guys be quiet? I can't hear you. Isabel, what was solve for MA? Right here. The definition of MA is force 2 over force 1, so I just put in what force 2 is and what force 1 is. I'm sorry, I still can't hear you. Okay, solving for X. Okay, so solving for X, I had my definition that MA is also equal to L1 over L2. And so in my picture, I defined L2 as X. And so L1 is going to be the total length minus X. And so in this equation, I just multiplied both sides by L2. So I had L1 is equal to L2 MA. And then I substituted for L1 and L2. So I have L minus X in the place of L1 is equal to X in place of L2 times MA. And then I just moved the X across, adding X to both sides. And so then I had L is equal to MAX plus X, factored out the X from the right side. So I had L is equal to X times MA plus 1, divided by the MA plus 1. And I have my value for X. Yes, Randy.
I got a 0.23.
I don't know.
I don't get how you got it. It's 1.33.
1.33 is the total length. 4.71 is the mechanical advantage.
It's 23.
Right. So how is the bottom? How is the 4.71 already
In what?
centimeters?
No, it's not. It's unitless. The top is the only thing that has units there.
Why do I have to convert? Why do I?
Because it asks for the answer in units of centimeters.
That's all. 20.
Okay. Okay, let's get on with things. So we've done this leverage problem. There are more simple machines besides the lever. Yes, question?
Does the mechanical advantage have a, like, units?
No, it's unitless. Okay, other simple machines. This picture on the left is an example of, well, what you and I would probably call a ramp, but what physicists call an inclined plane. Yes, inclined plane is a type of simple machine. You can have, in this case, a barrel that weighs 400 pounds. How many people can deadlift 400 pounds?
I can.
Okay, we have a surprisingly large number of people. I am sadly, I don't think one of them. But if you make a ramp, you can make that ramp so it's really flat. And so then the component of gravity you have to push against is just the component of gravity that's going down the ramp. So the flatter it is, the smaller the component of gravity you have to overcome, right? So you can have a much smaller force to roll it up the ramp. But you always give up something. You have to push it a much longer distance. So the total work is going to be the force you apply times the distance it moves parallel. It's going to turn out that it's the same thing. So let's actually just do the calculation real quick. We have a force of gravity like that, like this. That was perfect. Like this. Force of gravity is mg. And so I'm going to break that force of gravity into components like this. Well, x and y like that. And so my force of gravity is going to be, there's the angle of the incline. This is the opposite side, so that's mg sine theta is the force of gravity I'm opposing. So if I'm in equilibrium, we always do our calculations for simple machines as if you're doing it in equilibrium. So if I'm in equilibrium, my upward force up the slope is going to have to be equal to that downward force, so there's no acceleration in that direction. So my force 1 mg sine theta. And then what's the distance I have to push that thing? Okay, so if this is h, and that's theta. How do I get the distance based on h? Opposite side and hypotenuse is which trig function? And so I'd have, can you read that? Is the contrast good enough?
Yeah.
Okay. Sine theta is opposite, thank you, h over the length I have to travel. And so the length is equal to h over sine theta. So the work is equal to the force times distance parallel, which is force 1 times L equals mg sine theta times h over sine theta. Look what happens to the sine thetas.
Disappears.
They cancel out, and it's equal to mgh. If I lifted it straight up, how much work would I have had to do? mgh. It's the same work. I had to push it a much larger distance with a much smaller force. Dave?
Isn't that the calculation potential energy?
mgh, yes. That's how much work it would take. The change in potential energy is well, minus, but yeah. Yeah, that's exactly right, Dave.
I'm confused about how that kind of works out, but okay.
Well, this is the definition.
Change in potential. Never mind. Okay, we're good.
Change in potential energy is minus work.
Gotcha.
So the change in potential energy is mgh, which is... Okay, so that's one type of simple machine, and it's pretty easy to understand why that's useful. Right? Anyone who's loaded a moving van knows it's a lot easier to roll these things up the ramp. You got that refrigerator than it is to go heave ho. This thing over here, the old pulley system. That's another simple machine. It's a very different simple machine, though. With this pulley system, if you look at this carefully, what you see is you have a rope that you pull here. So this is the force 1. Okay. I'm back this way. There's the force 1, and then we're lifting this here, the force 2. I believe you that you're doing it, because I sure as life am not. So how is this thing going to work? Any ideas?
Lots of pulling.
Lots of pulling. When I pull on this rope, remember a rope makes a force that is equal to the tension in what direction? The direction that it's pulling away. So if I look at this lower pulley, this upper pulley is fixed. So it's not part of what's moving. This lower one is. So if I look at this lower pulley, what forces do I have on it? I have how many strings?
6.
I have 6 going up. So I have 6 upward forces, all tension, so that those add up to 6 times the tension. I have 6 times the tension pulling up. So I put in a force of tension and it goes up with 6 times that force. Which means that if I pull with a force of 50 newtons, how much force can I raise? 300. So yeah, it's the mechanical advantage is 6 here.
How are all 6 of the strings going up? Like, are they going down?
We just look at the direction the string goes from the object. So all of them are going up away from the object. Right? Because the string applies a force anywhere it touches the object in the direction of the string. So the top one, it's pulling down on each side. The bottom one is pulling up on each side. And that's part of the mechanism of tension.
And I'm pulling you. I'm pulling you. Even though it's tension, like my hand is pulling. It's not pushing. Right? So they're pulling up.
So in this case, since you have a mechanical advantage of 6, what's the easy way to figure out the mechanical advantage? Just count the wires. Yeah. So we have a mechanical advantage of 6 here. If I want to raise the load 1 foot, how much am I going to have? How long am I going to have to pull the rope? 6 feet. Now, I mean, I can tell you when I was a kid, I was like 14 and my dad had me buy this beater car for $200. The engine didn't work, and so I had to pull the engine out. And, you know, I'm thinking this is impossible. I'm 14. I don't know much physics. My dad brings this, you know, block and tackle thing. Here, pull on the chain. Okay. It was really easy. Why was it easy? Because I had a mechanical advantage of like 8. And so I didn't have to put nearly the force of the engine to lift it up because of the simple machine. So those are 2 examples of other types of simple machines. Another type of simple machine, a screw. A screw is, if you think about it, a rotating inclined plane. All right, now I did that intentionally. This is the last slide we had in class yesterday.
Wow.
We are getting on to new material now.
Yay.
Indeed, yay, that's what I said. So, first, another example of the right-hand rule. This goes with what Oksana's been saying we've been doing. You can determine the direction of the angular velocity. Angular velocity has a direction, has the word velocity. By using your right hand and wrap your fingers the direction it rotates, and your thumb is the direction of the angular velocity. So, if Sarah sits and spins, what direction is her angular velocity right now? Down. Wrap your fingers the direction she's rotating, thumb points down. Just make sure you're using your right hand. Thank you, Sarah. I know you volunteered for that. So it's pretty easy, right? Using the right hand rule to determine the direction there. And if you think about it, that's the same way we were doing the torch with the way Oksana said. What direction would that force make it rotate? Right hand rule. Angular momentum is in the same direction as the angular velocity. Just like linear momentum is in the same direction as linear velocity. So when Sarah was rotating, since her angular velocity was down, what direction was her angular momentum? Down. It seems somewhat confusing because was she moving down? No. So the angular momentum is not saying the direction it's moving. It has something to do with the direction of the rotation.
What was my angular velocity then?
Because you were going like this, you take your right hand and you wrap your fingers the direction of rotating, and the thumb points down.
That's the way.
Okay. Moments of inertia. You remember when we talked about Andy, I even used Andy's name coming up, so y'all remember. When we talked about Andy, we talked about her having a moment of inertia that was much bigger when she had the masses out here, much smaller than they were in. And I said it turns out that the moment of inertia is mass times the radius squared, where the radius is the distance from the axis of rotation to where the mass is. Well, here is that equation written out mathematically. If you have more than one mass, you have to add up mass times radius squared for each mass. So that sigma out front, that means sum, adding all of them up. Subscript I is just adding up of all the items that exist. Mass of item times radius of item squared. So in Andy's case, ignoring Andy's body, she had 2 masses. She had mass 1 times the radius 1 squared plus mass 2 times radius 2 squared. Why am I ignoring Andy's body? Because her body's complicated. It's got mass all over the place. That was in no way meant to be anything other than a truthful statement about how any solid object has mass all over the place. Y'all laugh like I do. Okay, so to actually calculate the moment of inertia for Andy, we would do it experimentally because it's just too complicated otherwise. But for things that are uniform objects, like, say, this is a hollow sphere. The hollow sphere is uniform. We can use calculus, and we can calculate the mass distribution and get an equation for the moment of inertia. And we started to do that in the calculus-based physics class this morning. We didn't get very far, though, did we, fellas and lady? So here is a table that, of course, comes from the textbook of the moments of inertia for different shapes. Now note the moment of inertia depends on the axis you're rotating about. If you rotate, Annie was rotating about her center mass. If her left hand was fixed and the right hand was going all around that, it'd be a much bigger radius for the one of them, a zero radius for the other. And the moment of inertia would turn out to be much bigger because it's proportional to radius squared. So you look at these and you have, here is a thin rod about an axis at the end, a thin rod about an axis at the center. The center you have ml squared over 12. The end you have ml squared over 3. That's 4 times bigger. So like on the test, you'll have this table. And so you'll have an object. If it's a ball, if it's a solid ball, you look up here and you look for the solid sphere about any diameter. So you use this table because otherwise you need calculus. On the left side here, I have all of the equations we use in rotational dynamics. This one here is not rotational, it's a starting point. But instead of saying kinetic energy, it now says kinetic energy trans. That means translational. Traveling in a straight line is what we call translational. So we have the translational kinetic energy. If you have something that's rotating, for any piece that's rotating, you know that its velocity is omega times r. And so I can say that piece's kinetic energy is 1/2 mv squared, or 1/2 m times omega r quantity squared. And then I just distribute that square, and I have 1/2 mr squared times omega squared. That's where the mr squared comes from the moment of inertia. So this right here, we replace with I. And so that was for one piece, but now I can be for the entire object. We're just counting all of the pieces. As long as it's a rigid object. That is, it's not something that's squishy and some parts are rotating faster than others. They have to all be rotating together.
What if it's all switching?
Then we're not going to do it. And when I say squishy, I mean different rotational rates. Okay, then we have L. L is the symbol for angular momentum. Angular momentum, what I had on the previous slide was angular momentum is I omega. Moment of inertia is I, the rotation equivalent for mass. And then omega was the angular velocity, rotational equivalent for velocity. There is a second equation there. L is equal to R cross P. Notice I said cross. If you have two vectors, it doesn't mean multiplication, it means multiply the perpendicular parts. How do you find the direction from that cross product? The right-hand rule.
Can you use the
Generally speaking, not as easily.
That's okay.
But you have the radius and the momentum to calculate. So if I have this ball and it's falling, and I want to find its moment of inertia about this point right here, I can do it. Because if it's falling, what direction is its momentum? Downward. So if momentum is downward, I have R cross P, so R is going to be the perpendicular distance to down, so R is this distance here. Even when it's up here, the perpendicular distance is the same. And so I just take the R perpendicular times momentum, and then to find the direction, I have to use the right-hand rule. So my index finger points that way, middle finger down, because that's the direction of the momentum. My thumb comes out. That's the direction. So this ball falling can be, you can calculate any momentum about some point. Great. That's a demonstration for later today. It's not going to involve me falling down. And then we have the torque equation we've already seen. Newton's second law that clearly we've already seen a lot of. And then the rotational equivalent. And once again, I write it as a vector equation. You know, if that guy goes and listens to more of my lectures, you might say, oh, look, there you are, you're doing it again and again and again. It's because fundamentally it works. Just remember that the moment of inertia is different about different axes. And so for this, if I rotate it about this axis, it's a different moment of inertia than if I rotate it like this. And so this equation has different moments of inertia depending on which vector direction you're using. Those are our equations. What we have to do is figure out how they work. So, how do we solve problems that are rotational dynamics? Okay, so he's looking at the steps already. First, draw a diagram. And that was no shock, right? Now I'm doing this with the forces and torques method. So you draw the diagram, identify the rigid object that you're talking about, draw a force diagram showing all the forces where they act, apply sum of the torques equals I alpha. Now we've actually seen this. Right now we've actually seen the equation, haven't used it yet, but we at least know it. Apply Newton's second law, find a relationship between acceleration and angular acceleration, solve it, and make sure it makes sense. The steps at this point, they should be starting to feel a little more comfortable, even though this is an all new set of steps. It's fundamentally similar, right? In fact, for using the work energy, it's exactly the same. Rotational work is one last equation we need. Remember, when you're using work energy relation, you're going to need to have a way to calculate work. And so for regular old work, it was force times distance parallel. Remember the whole thing, I'm carrying it like this, there's no work. For rotational work, it's torque times the change in angle. Torque, the rotational equivalent of force. Change in angle, the rotational equivalent of change in position. And conveniently enough, obviously it has to be torque in the x direction and change in angle in the x direction, defined using the right-hand rule. But those are pretty much always going to be the same, right? So work is equal to torque times change in angle. You think about the units. What are the units of torque? Newton meters. What's the unit of angle? Radians, which is unitless. And so you take Newton meters times radians, and the Newton meter becomes a joule.
What? Why is it a joule?
Because it's work now. The same unit, but it was called a Newton meter when it was torque. It's called a joule when it's work. Sorry to frustrate you, Sarah. All right. Some cool. This picture here cracks me up. I don't know. This is an experimental vehicle where you have a big old flywheel that you get spinning and you use that to drive the bus. But our cars do this too. Your car has a flywheel. Depending on your car, it might have a bigger moment of inertia or smaller moment of inertia. But what's the point of that flywheel? You have something with a moment of inertia and it's rotating. That means it has a kinetic energy of 1/2 I omega squared. And so you're storing energy in it in rotational energy. So in a normal car, if you just let off on the gas, the engine doesn't just go down to, it's I RPM. It comes down slowly because you have the energy in the flywheel keeping it going. So it helps to balance speed. And also makes it so you don't, especially at low RPMs, you have the cylinder fires and this cylinder fires and this cylinder fires. You don't feel jerky, jerky, jerky every time one cylinder fires. It smooths it out. Question?
So shouldn't that be omega squared?
Well, that's just saying it's rotating. The kinetic energy is 1/2 I omega squared. But that's just saying it's rotating. So it's a way we can store energy. We've already gone through this kind of action, right? Andy did our example here of being the figure skater. And in the case of Andy, I said angular momentum was conserved. Why was angular momentum conserved? What condition do you need for angular momentum to be conserved? Okay, that was linear momentum. And we're going to take the straight analogy on that. So Newton's second law for the linear case was net force is equal to change in momentum over change in time. For the rotational case, it's net torque is change in angular momentum over change in time. So if I solve that equation for change in angular momentum, I get this. So what conditions would make change in angular momentum 0?
Zero torque.
Zero torque, or, and no one ever talks about this, 0 time, because you know, collision, you say the collision is a very short time. A rotation, you don't say the rotation is a very short time. So if the one, I know I have a space for 2 of them on your answer sheet, but the only one that really matters is the net torque is 0. So in Andy's case, she had her feet not on that bar, so she had no torque about the vertical axis. There was nothing to speed her up or slow down about the vertical axis. What about a horizontal axis? If she leaned to the left, that chair isn't just going to fall over. It's going to supply an upward force to keep her from tipping over. So it's going to supply a counter torque. So her net torque about a horizontal axis was not 0. So angular momentum would not be conserved in these directions. But it was conserved about the vertical axis, which means rotation about that axis that was conserved. Now, Annie, come help me again.
Do I need my chair?
Yes, you need your chair.
Yes.
So this is a bicycle tire that has a bunch of copper wire wrapped around it. The copper wire makes it so you have a bunch of mass far away from the center. Why? What's the point of that? Yeah, go ahead and set down.
Equilibrium.
No, not equilibrium. What would the point be of having a lot of mass as far away from the center of rotation as possible?
More weight.
More moments of inertia. More moment of inertia, because remember, it's mr squared. The bigger the r, the bigger it is by a factor of r squared. So we're going to hold this up, and I'm going to spin it. And you put your feet down, unless you're comfortable with it. So I'm going to spin it. What direction is the angular momentum of this tire right now?
Negative.
That way.
It's pointing that way. It's pointing to her left. Okay, now lift your feet. I know that, dude. Now rotate so the angular momentum points up.
Oh, right.
Okay, she rotates so the angular momentum is pointing up. But what's she doing? She's rotating with the angular momentum that's down. Now you can see there's some friction because she stopped.
What?
You can after class. Because angular momentum about the vertical axis is being conserved, there's no torques about the vertical within limits. As she changes this to have different angular momentum in the vertical direction, her body has to compensate by rotating to keep the total angular momentum in the vertical direction the same.
Just random.
Is that cool or what?
Just randomly rotating.
It ain't random. She's controlling it.
What's making it rotate?
Her hands are. She's twisting.
Not the. What makes her body rotate?
Oh, that's conservation of angular momentum. Because this had angular momentum that was initially pointing to the left, the amount in the vertical direction was 0. Then when she rotates this so it has angular momentum pointing up. It's not good. If this has angular momentum pointing up, the total angular momentum has to be 0 still. And so she has to spin with angular momentum down to counter the angular momentum of this pointing up, to keep it at 0.
That's why. I'm good.
So,
Can we do it again?
can we do it again? This is useful in things like gyroscopes. A gyroscope, you spin it really fast, and then it's going to try to maintain its angular momentum. And so you can use that to detect changes in angle.
Put a 180.
Yes.
And for orienting
Turn around.
satellites.
And for orienting satellites or orienting drones, because Nathan just bought a couple. Yeah.
Stabilizing firing systems.
Sure. Okay. Yeah. I'm done with you playing. If you guys want to play after class, you totally can, because you know it's physics, and that's what we do in physics, right? We play.
We're not playing.
Hey, don't cry. I'm going to be like Tom Hanks here. There's no crying in physics. That yes. There's no crying in baseball. In A League of Their Own, one of his famous quotes is, "There's no crying in baseball because one of his baseball players is crying."
Crying is important and healthy for everybody.
Okay. A note of mental health: crying is important and healthy for everyone. Moving on. Conservation of angular momentum is really important when you start saying things like astronomy. Because if you're talking something like a cloud of gas isolated out there, there's no external forces to make torques. So it's going to have its angular momentum conserved. So if it's slowly spinning around, but then gravity makes stuff fall in, what's going to happen?
They're gonna get faster and faster and faster.
Right, because the moment of inertia is dropping, the angular velocity has to go up. Now, thinking about this, let's go back to Andy yesterday. Andy had these masses out here, she was spinning around. When she brought them in, what was conserved? Angular momentum. What about her kinetic energy? Apparently not, because you read ahead. Well, what is the equation for kinetic energy? Rotational. I omega squared. 1/2 I omega squared. So if we put, since we know the angular momentum is I omega, then we could say that this is equal to 1/2 L squared over I. And so since her angular momentum stayed the same and I got smaller, her kinetic energy, what happened to her kinetic energy? Well, if I get smaller and L stays the same, it increased. So her kinetic energy increased.
Oh.
Why, which is one of your questions, why did her kinetic energy increase when she brought them in?
Because you sped up.
Well,
I changed my lid.
let's talk about energy. Energy can't be created or destroyed. So what would make her kinetic energy go up? A loss of potential energy would, but we didn't have any in this case. So that's a fair answer, but it's not the correct one here. We're assuming no friction here. Andy, when you brought them in,
Did she change the radius?
did you have to pull them in, or were they falling in and you had to push them out?
I had to pull them.
She had to pull them in. So she was applying an inward force, and it moved inward. She did work. And that work she did translated to her spinning with higher kinetic energy.
That's crazy.
Is that technically like an external force?
No, it was actually an internal force, but it was redistributing energy from Andy's body to her rotation.
So if you
It's like
have,
when you jump into the same.
let's say you have like an arm extender, right? And you moved it in even more work, you moved it even more faster.
Yeah.
That's crazy.
Okay, Oksana, what was your question?
So is omega a unit vector?
Is what?
Is omega a unit vector?
More faster.
No, omega is a vector, not a unit vector. Huh?
It wouldn't be a unit vector.
Right, a unit vector has a magnitude of 1. Omega can have any different magnitude.
Over.
Okay, so if you have something like the collapse of a star into a neutron star. Neutron stars are former stars, they're not stars anymore. But what you have is a star collapses down until a white dwarf is electron degeneracy. A neutron star, neutron degeneracy is what keeps it from collapsing even more. But it collapses down to be like 15 kilometers across. So imagine something that's like 10 times the size of our sun suddenly collapsing to be the size of Lincoln.
Yikes.
That's a big collapse. And it was spinning. You know, our sun spins. What's going to happen to its rotation rate? It goes really fast. So when Jocelyn Bell discovered the signal they called the LGMs, the little green men, it was a very fast pulse. And they started calculating what could it be. And, well, yes, pulsars is the name for them. And they came down to the only thing that could possibly pulse this fast would be a neutron star spinning really fast. Why spinning really fast? Because if it was rotating before it collapses, it's going to be spinning really fast after it collapses for conservation of angular momentum.
Can you clear this out?
So the reason kinetic energy isn't conserved is because work was done?
The kinetic energy increased because she did work. She did work on the system, adding energy to it, adding mechanical energy to it. Okay, now we had Andy up here doing some actions. We're not going to do this one with Andy just because it's a little harder to simulate. But you're riding a bicycle. And you ride that bicycle and you lean. What happens when you lean?
Death.
It's not death.
Depends on where you're at.
That's kind of a pop song from the 80s?
Eileen.
To the topic of the day. If you're riding your bicycle, you're like no hands, look at me, and you lean to the left, what happens? You turn to the left. Somebody said fall. If you lean to the left, you turn to the left. Why? This is physics. So let's do a problem. You're riding your bicycle forward and are showing off by riding no hands. Funny story ever. My brother changed the front tire of his bicycle. He puts it back. This is when he was like 8. He's riding down the road. Look at me! He pops a wheelie. The front tire goes rolling down. Okay. So you're riding your bicycle and you lean to the right. What happens? So we got a bunch of steps to doing this. As easy as falling off a bicycle, I call it, because I thought I was funny. I was tired at that point. Obviously, since I made the mistakes earlier of deleting stuff I didn't mean to. So what concept is involved with a question like this? What was that? Rotational dynamics. Absolutely, it's rotational dynamics. Now, this one here is going to be solved differently than what I said before, because we're not going to be asked to find what's the torque or what's the force or anything like that. We're just asked, like, phenomenologically, what's going to happen. So draw a diagram showing the situation is viewed from above, and then it's viewed from the rear. So the top view, there's my tires. Here's the rest of my bicycle with the person on it. There's my top view. A rear view, here's the tire. Here's the person sitting on it. Okay, so those are my two pictures to begin with. Pretty basic, right? No one claimed I was an artist, or at least I did. And no rational person did. So we're going to have to add things to this diagram as we go on. So first, when you ride a bicycle in the forward direction, what direction are each of the following? What direction is the linear momentum of the bicycle when you are riding it?
Forward.
Forward. Okay, so on the top view, that's easy. The top view, there's my linear momentum. On the rear view, well, you could go like this. That's how we indicate that it's moving away from you, a circle with an X in it. The X is supposed to be looking at the fletchings of an arrow. So the arrow is pointing away from you and you're seeing the back end of the arrow.
And then what's P?
P is momentum. So the momentum vector is pointing away from you is what that means.
Got it.
Okay, so go ahead.
What is the circle X?
That means away from you. Right, this here means toward you. That's supposed to be a circle with a dot in it because you see the arrowhead coming toward you.
Why are they using arrows for this?
Because we use arrows for that.
Point.
Right, this here's an arrow.
Oh.
This is an arrow going away from you. And an arrow going toward you.
What about that?
Those are conventions so you can understand when you see the diagrams.
The dot is toward you.
Yes.
Yes, think of an arrow.
Okay, so we got the linear momentum of the bicycle is going forward. What about the angular momentum of the tires if you're riding forward?
Momentum of the tire.
Yes. So I'm riding forward. It's rotating like this, man.
So where's fast forward?
Whatever I'm facing is considered forward.
Oh my goodness.
The top view is to the left.
So
Facing the child.
is it pointing? What direction is it pointing?
To the left.
Towards,
Toward my left.
Yeah.
Right? It doesn't matter which direction I'm going, it's going to be pointing toward my left.
Because the radius is out this way, and then the force is going around.
Well, in this case, we're not doing a force. We're just wrapping our fingers the direction it's rotating.
Conceptually, that helps me.
Towards the east, so it's gonna do that.
To the left.
Otherwise, I'll get confused by the right hand.
Right hand.
Well, there's different ones. As we go on, we'll learn a couple more right hand rules next semester.
I thought they were.
So, angular momentum is pointing to the right or the left. So in my picture, notice I was clear about the top view here and the rear view. So the left is going to be, what's the symbol for angular momentum? No, W is the angular velocity. I is the moment of inertia. L. So I'm going to have L is pointing to the left, which I can indicate on both of them. So I've got 3 answered. Number 4, when you lean to the right while riding forward on your bicycle, what direction is the torque applied by the force of gravity about a point of contact between the front tire?
So the direction, wouldn't it also, hold on. 'Cause down-
Lean to the right, so here's the bicycle to the right.
Toward down right, so-
We want to sum the torques about this point. We have the force of gravity. What direction is force of gravity?
Down.
I mean, yeah.
So it's negative.
Okay, I want to be a little more clear than negative and positive. This is from the rear view,
Okay.
and so if you have your, I gotta stand so I'm with you guys, back to you. Fingers like that for the R, middle finger pointing down, thumb is going
Forward.
forward. That's right.
Wait, come again?
Because this is a view from the rear,
I'm stupid.
you're not stupid. Yeah. So I get my right hand. R is going from the place I'm summing the torque to where the force acts. So my R is pointing like this. Then I need to keep my index finger that way and orient my hand so my middle finger can point the direction of the force of gravity. My thumb points that way. Since this is a rear view and my front.
Do it again. Get lost.
Okay. Index. No. Index finger has to point the direction of R. So R, I'll draw the R on here just so we're, there's R, right? So index finger is pointing this way. Keeping it pointing that way, I rotate my hand so I can bend my middle finger in the direction of force. My thumb is pointing in, and since this is the rear view, in means forward.
Yeah, because you could maybe go down this way.
It has to be in the direction between index and palm.
Wait, I thought they had
What?
No, these are all
Yes. Well, okay. The first 2 don't have to be perpendicular. The third one has to be perpendicular to the first 2.
Wait, but how goes down the
Okay, so your index finger is pointing like this, right?
right? Yeah.
And then you keep it that way, and I need to bend my fingers toward my palm so that they point in the direction of FG. So this is the only way I can bend them toward my palm, point in the direction of FG. Okay. So then what direction is the torque? We said it was going forward. So in the top view, I can draw the torque easily enough. The torque is going to be like that when I lean to the right. In the side view, it would be like that as my torque. And keep in mind, these are the torque if you lean to the right. If you lean to the left, what would it be? The opposite. Okay? So we have the direction of the torque when I lean. If you're not touching the handlebars, what direction will the angular momentum of the front tire change toward? This is where we get to something we got to think about. I want to find change in angular momentum. But we just had this. When we talked about the condition for angular momentum to be conserved, we had an equation. What was that equation? Yes, torque net multiplied by change in time. Not in this case because I'm leaning to the right. Since I'm leaning to the right, my net torque is forward. So what direction is my change in angular momentum going to be? Forward. So now let's look at the angular momentum. We started with the angular momentum pointing to your left. And then we have the change in angular momentum is forward.
Why is it starting to my left?
Because you were going forward in the right-hand rule. So now it's going forward. What's the tire going to have to do to make the angular momentum go from pointing left to pointing forward of left? Here's my tire. It's spinning like this, so the angular momentum is going left. If I want to make the angular momentum point forward, what's it going to have to do?
Turn to the
It's going to have to go like this. And so that's why the tire turns when you lean right to make you turn right. Now that brings up some other really interesting things, which you've probably seen before. So you take this and you can go like that, and it spins around. Why is it doing that? If I change the speed, I can make it go higher,
Let that go.
or make it go lower. Why?
Because of angular momentum.
I'm applying torques, and if I apply torque, it's going to make the angular momentum change. And so I can make this pop up or go down by applying different torques. So it's really cool. One of the coolest things, back in the day, instead of having like practical or impractical jokers and stuff like that, we had Candy Cam with Allen Font.
This is new. Sorry.
And one of the funny things they did was they took a suitcase and they put a tire in the suitcase with a little motor to make it run really fast. So this thing is spinning really fast. So you can see with this, if I take this and I try to turn, it goes into me like that or it goes up the other way. Well, they have this in the suitcase, and they go through the airport, and they have somebody, set down the suitcase and ask some guy, frail lady, ask the guy, "Could you carry my suitcase for me?" And so he picks it up and he tries to keep, she goes around a corner, it flies out, the guy's like freaking out, like, what's going on with this? Physics, right?
You can't do that now.
Do what? Yeah, I know, you couldn't do that. But then they actually did other things that are even more cool. They decided that was good. Here's another idea. Let's put concrete in the suitcase. And so they have a suitcase filled with concrete, and a little old lady, "Could you carry it for me?" People going, ugh, ugh. It was all funny until this big Russian dude just comes and picks it up and starts walking. And they're like, okay, we didn't expect people to be that strong. But physics, they said, now this one costs more money. They dug a hole in the parking lot, they put an electromagnet in the parking lot, and then they covered it back up, passed it up, and then they put an iron sheet at the bottom of the suitcase. So the suitcase itself wasn't that heavy, it was like 20 pounds. But they have electromagnet to turn off and on. And so then when they see a mark come, the little old lady, she sets it down on the electromagnet and then they turn it on. And then she asks the guy to pick it up and he's like, I can't do it. She's like, well, it's not that heavy. She picks it up and sets it back down. Physics is great, isn't it? Those are physics things we'll learn about next semester, the electromagnets.
I have a question.
Go ahead.
Okay, so in a motorcycle class, they say that if you're doing a high speed,
Mhm.
you press on the handlebar.
Yes. The first time a student asked me this question, I was like, I don't know. I don't ride a motorcycle. I had to go think about it. Okay, so does anyone here have experience riding a motorcycle on a highway?
I crashed.
Well, a crotch rocket you probably did as a kid. I don't know.
I crashed.
Oh, you crashed. Well, that doesn't count. I have experience, sure. I got the hospital, don't prove it. Okay, so what Andy is saying is, when they're teaching you to ride a street bike, they teach you when you're at freeway speed, if you want to turn to the right, you don't lean to the right, you push the handlebar forward on the right.
What?
Yeah. When a student told me that, I was like, what? That doesn't make any sense. But it does.
It feels so counterintuitive.
It does, because when you push it forward to the right,
You push the right side forward.
Yeah, you push
So
the right
like the
side
wheel would
forward.
turn to the left,
Yes.
but you go right.
You push the right side forward,
Yeah.
and it's going to make the bike lean to the right.
At highway speeds.
That makes sense.
Yeah, at highway speeds, yeah.
Anywhere else, you kind of just.
Yeah, anywhere else you just turn it yourself. But at highway speeds, you have enough angular momentum involved here that if you try to turn it yourself, you're probably just going to knock yourself down.
Why don't you lean?
So, huh?
Why don't you lean? Just lean your body.
Hey, I don't know.
That's because.
But you push it this way, so you're creating a torque that is upward. And so then that upward torque is going to make your bicycle's angular momentum that's to the right tip up, make the whole bike tip to the right, and that makes you turn right. So you're actually forcing the tip by pushing it forward.
Okay.
Yeah, like I said, it seems so counterintuitive. The first time a student asked me, I was like, I was not aware of that. Okay, so we finished that problem, right? We're down to the last problem. Yay! 3 objects of equal radius are rolling down an inclined plane. And we're going to do this, of course.
Wait, go down the last
What
round.
direction is the angular momentum?
Which question are you asking?
5.
5. If you do not touch the handlebars, what direction? Remember this picture right here? So your angular momentum was to the left, but it has to move forward, which means that the tire has to rotate this way because the angular momentum is always going to be pointing to the left of the tire. So to make it go forward, the tire has to rotate that way. Okay. So last problem, 3 objects of equal radius are rolling down an inclined plane. So I'm, of course, until the end, only going to do 1. So here's an inclined plane. Ta-da! Simple machine, right? Cool. Oksana.
The answer.
Let's talk about it later. We only got 20 minutes left in class. Okay, so what we're going to do is we're going to do a race between 3 objects. They're just going to roll down. And the question is, which one will reach the bottom first? Tennis ball, solid sphere, or solid cylinder?
Neither.
No, it doesn't depend on friction. Notice it says that they roll without slipping. So that means friction is high enough that none of them slip. If they slipped, it would be different, yeah. Okay, we have a conjecture of the one with the highest mass.
Acceleration is equal to tennis ball force times.
We have an answer of tennis ball.
No, wait. I take back.
Take back tennis ball.
Is
Well,
it a sick thing?
what we want to do,
With viscosity?
this is fundamentally the same as the viscosity one. Yeah?
So is it acceleration equal to mass times force?
No. If you had no friction at all, then they would all go down at the same rate because they'd all have the same acceleration that would be g sine theta. But this has friction and it's rolling. And so what's going to happen? There's 2 ways of solving this. One is doing the work energy method using rotational dynamics. One is doing forces and torques using rotational dynamics. Which one do you suppose is easier?
Torque.
So I'm guessing rotational torque since it's a section.
Work energy is the easier one.
Wow. Okay.
Work energy is almost always the easier one. If I could do it, I could say the sum of the torques is equal to I alpha, and then I could calculate what the forces are, and I can work it out that way and calculate the acceleration of each one. Or I can do the work energy, and that's the way we're going to do this. And we're only going to do it one way because we don't have enough time to do it both ways. So, what's the concept involved? Rotational dynamics. 2 ways of solving this.
Work energy.
Walk energy, close enough.
Yeah.
Work energy or
Yes.
Some of the torque.
or let's just do forces and torques. Right, Newton's second law. Newtonian dynamics. Draw a diagram showing one object starting at the top and rolling to the bottom. Only going to show one because the calculation will work for all three. So what should my diagram look like?
A triangle with yeah, kind of like that. And then a circle right there. Yeah.
Yeah, it's a circle.
And then
In a matter of speaking.
pointing down.
Well, it's
Circle, arrow, circle, arrow, circle, arrow.
like that. Fine. Okay, start and bottom. And then it says identify the equations for kinetic energy, potential energy, and potential energy at the top of the ramp and the bottom of the ramp in terms of I, M, V, and Y. I should have put omega as well. And R. Sure, why not? Excuse me?
1/2 I omega squared.
Okay, so kinetic energy, rotational initial, it's 1/2 I omega initial squared. What's omega initial?
0.
0, because it doesn't say specifically here, but yeah, it says right there, starting from rest, it does. So that's equal to 0. What about translational kinetic energy? 1/2 mv squared, which is 0. And what about potential energy initial? Notice there's no rotational equivalent to potential energy. Yay.
So,
Okay, mg, and I'm using y for the vertical direction, so mgy. H is y. And y initial. Okay, what about in the final case?
yeah, 1/2 IWF. I swear to God.
What's the translational? Okay, the potential energy final equals 0 was a statement made by Max. That's why I wrote it down when he said it. That's assuming that we use this is y equals 0 at the bottom. Okay, so I have that. All of those equations done. Calculate the work done by friction. This sounds tricky.
It's equal to negative something.
It's all the words, right?
Negative change in change. Negative.
Okay? That's a correct rule, except for it's not conservative. But
It's equal to the change in potential energy plus the change in kinetic.
it's force times distance, right?
Parallel.
And this is parallel, yes. So at the point of contact, how much distance do we have of motion between the non-slipping surfaces?
0.
0. There's no work done by the force of friction. It is going to actually transfer energy from one type to another, but it's not changing the overall energy. It's just transferring energy. So we have no non-conservative work done by it. So if the word non-conservative is 0, you always have to calculate that, because if it wasn't 0, it would be important. Apply the work energy relation.
0 again? Why?
Because there's actually no motion between the two surfaces.
Okay.
The point of contact is stationary as it rolls down, because it's not slipping.
Makes sense. If it was
Oh,
slipping,
okay.
then it'd be like, it would take away.
Yeah, then it would take away energy.
Gotcha.
Since it's not slipping.
But what it's doing is it's the vector through which you transfer potential energy into rotational kinetic energy. Okay, so now we do the work energy relation. I didn't give myself room for that at all. Didn't give you room for that, so you have to find place. But we have work non-conservative is change in kinetic energy plus change in potential energy. We just calculated that was 0 for the work non-conservative. Change in kinetic energy, that's going to be these two final minus these two initial, right? So that's 1/2 I omega final squared plus 1/2 m v final squared minus the initials, which were 0. And then plus change in potential energy, which is 0 for the final,
Minus MGY.
minus the initial. Well, when you do this, notice the variables we have. We have I, omega, M, that's M. V final, MGY. But we can combine some of these. Because it's an object rotating, we know that omega, well, R omega is equal to V. So that means I can say that omega is equal to V over R. And so where I have omega finals, V final over R. So now I have one variable, the omega, that's disappeared. And my problem asked me to find V final in terms of the remaining variables. So let's rearrange. I have 0 equals V final squared times 1/2 of I over R squared plus M. Notice I factored out the 1/2 as well. I just factored it out separately because in the end I'm looking for V final. And then I have still the minus MGY0. Through the magic of using an erasable marker, I'm going to add MGY0 to both sides like this. What's my penultimate step for solving for V final? Yeah, divide by things in the bracket.
Then you need to square root both sides.
And that's the ultimate step. Okay, square root came out a little too big. So there's my equation for V final in terms of the variables. So we have this. This works no matter which object we have. But now you're instructed to put in the different i's. So if I put in the different i's, what's different about the moments of inertia? They all have mr squared, right? But they have a different fraction out front. So I'm going to have, for the tennis ball, square root of 2. I got to come over here because I don't remember. 2 MGY0. Like, all over. So the tennis ball was 2/3. 2/3 mr squared over r squared plus
Why did we have
M?
2 and GY initial?
Because I divided by 1/2. Dividing by 1/2 becomes 2 on top. So notice what's going to happen here. Somebody had said initially the one with the most mass. What happens to the mass right now? It cancels out. The mass isn't going to matter. Also, what happens to the radius? It cancels out. So here the radius is gone. Here the masses are gone. It's equal to square root. Notice in this case the 2's are going to cancel as well. I have 3GY0. Oh, wait, nope, can't put the 3 up there. 2GY0 over 2/3 plus 1. The 2/3 was in the moment of inertia. For the tennis ball, it was 2/3 mr squared. This m here, when I canceled the m's, it became a 1. No, that would be, no. M divided by m is 1. That's what we did. What was your question? I don't know. Okay, so if we put that together, that's the square root of 2GY0 over 5/3. Now I can put the 3 on top after I did it correctly. So that's for the tennis ball. What's different for the cylinder? The only thing that's different is the 2/3 becomes 1/2. So for the cylinder, I can short circuit my work. For the cylinder, and for the solid sphere, it's 2/5. So we have 2GY0 on top every time. On the bottom, we have 5/3, 3/2, or 7/5. The bigger thing we divide by means the slower speed. So the slowest one has the biggest denominator. The fastest one has the smallest denominator. Which of these numbers, 5/3, 3/2, or 7/5, is smallest? Okay, 3/2 is 1.5. What's 7/5? 1.4. What's 5/3? 1.67. So that means that it should be the solid sphere, then the cylinder, then the tennis ball. Time to do the test. Somebody want to come up and do it so you trust me? In case you don't trust me? You trust? Oh, the silly trust of the student thing. Okay, what scared me? There we go. Okay, so in that trial, it looked like these two were pretty much dead heat. And this one lost. Which one was supposed to win?
The
Solid cylinder. Okay. So this one here was clearly losing, right? Which it should. So let's just try these two against each other again. Part of the problem with the solid cylinders, you have to get aim just right. The solid cylinder beat the sphere. Is that the way it's supposed to be?
Yep.
Good. All right. Turn that in and go home.
Right.